Okay, hello everyone, and thank you for joining us for the ORI anniversary series. Today is like an honor and a great pleasure to have here Daniela Rus. And I think that the majority of you already know her for her amazing research work. But just to introduce her, Daniela is the Andrew and Anna Vitalbi Professor of Electrical Engineering and Computer Science. And she's the director of the Computer Science and Artificial Intelligence Laboratory at MIT. And she's also Deputy Dean of Research in the Schwarzman College of Computing at MIT. She is also a MacArthur Fellow and a Fellow of ACM, IEEE, AAII, and AAIS, and a member of the National Academy of Engineering and of the American Academy of Art and Sciences. She's also currently serves as a USA expert for global partnership in AI on the board of trustee of MVZUAI and on the British Telecom Technology Advisory Board and on the board of director of mass robotics. So her current research interests are in robotics and artificial intelligence. And also her key focus for research is to develop science and engineering of autonomy. So I think, thank you so much, Daniela, to be here with us. And I want to leave the stage for you.
Thank you very much for this really generous introduction and for inviting me. Let me see if technology works. Can you see my screen?
Yes.
Okay. Yeah. So when I was a child, my family spent some time in Stirling, Scotland, and this was before we moved to the United States. And I remember visiting Oxford and really admiring the student life and seeing the beautiful buildings and thinking how amazing it would be if I could someday be a student at Oxford. And so this is so much bigger and better than that. So thank you so much for having me with you today. Today, I'd like to tell you a little bit about how I have been thinking about robots in the recent past. And I want to start back to the days when I was a kid and I loved the science fiction books of Jules Verne and the movies of Jacques Cousteau. And some years later, after I learned to make and code robots, I met a student who also loved the books of Jules Verne and the movies of Jacques Cousteau. And we decided to build an underwater robot together. It was our own version of 20,000 Leagues Under the Sea of that observatory. And we call this robot Amour, which stood for Autonomous Modular Optical Underwater Robot. But really building this robot was about love. This robot was very lovable. It was agile. It was nimble. It was one of the first underwater robots that moved like a helicopter. The robot also took beautiful photos in color. It transmitted them using high resolution videos. All of these capabilities were enabled by new advances made by the students in my lab. Now, one very hot summer day after NICRA, off the coast of Singapore, we were there to test the optical communication system of the robot, and everything worked really well. And in fact, we ended the experiments one day early. And then we decided to take our third day on the boat to see just how fast this robot could go. And we were feeling very confident that day. We took off several safety components to give our robot more juice. And then off the robot went. Now, I should tell you that it took us 3 years to build this robot, and this was our only unit. And then we waited and waited and waited, but Amour did not come back. We lost Amour and we were devastated. Now, the thing about science is that the first copy of an invention takes enormous amounts of time to develop, but the subsequent versions take much less time. And it is also true that great failures teach us great lessons. So we went back to the lab and we worked all summer. And after 90 days, we made 3 improved versions of this robot. And then with great hope, we took the new Amour for a spin. And as we watched it make flips in water, we decided that we wanted more. And we began to imagine other versions of underwater robots. And that's how our soft robot fish was born. This is a robot with a soft tail that can flip back and forth for swimming. And you can see it here. The robot is able to change the swimming direction in about 100 milliseconds, which is about the same time as a real fish. And this is called the escape maneuver because it allows little fish to escape from the big fish who want to eat them. And so we took the soft robot fish to the ocean where we swam with it. And this is me next to the robot. And the robot swam elegantly past beautiful corals. It saw many schools of fish with its camera, and it even found Nemo. So it took 3 years to make a Moor, 3 months to make 3 copies of a Moor. And today we can make the soft robot fish in the lab in about a day. And this rapid change of pace of technology is really extraordinary. If you think about it, 2 decades ago, computation was a task reserved for the few because computers were large and expensive and hard to access. A person really needed a level of expertise to know what to do with them. But all that changed with a smartphone, and the smartphone democratized computation. Now computation is so normal, we don't even notice how much we depend on it. And to me, this raises an interesting question. In a world that is so changed by computers that help us with thinking work, what might it look with robots that could help us with physical work? How much work will we be able to offload to machines to save lives and to increase the quality of our lives? For instance, I believe that autonomous driving will give all of us the ability to go anywhere, anytime. And it is not a matter of if, it is a matter of when. And I might challenge you to see how many robots are there in this drawing. And the answer is 19. Now, enabling this future requires 3 interrelated fields. We have robots, which put computation in motion. We have AI, which gives machines the ability to reason. And we have machine learning, which enables machines to learn, improve, and make predictions. And progress really requires all 3 aspects. In fact, if you think about it, a robot is made out of a body and a brain. In order to have a robot capable of a task, you need the body that is capable of that task, and we need the brain that is capable of controlling the body, how to do what it's meant to do. And so today I want to talk to you a little bit about how we approach the hardware body of a robot and how we think about software. So let me start with the robot body. And let me notice that we have come such a long way with robots. This here is the Unimate. It is the first industrial robot which was introduced in 1961. And it was really quite a curiosity in 1961. It showed how one can do industrial pick and place operations. And by now, the number of industrial robots exceeds tens of millions. And these robots are in deployment. These robots build our cars and do so much more. These robots are masterpieces of engineering. They can do so much more than what we can. And yet these robots remain isolated from people on factory floors because they're large and heavy and dangerous to be around. And so a question that I have been asking recently is, how can we get robots to work side by side with humans? So in order to get there, we need better brains and better bodies. And now if you look at organisms in nature, they are soft and compliant and so much more dexterous and intelligent. Just look at this octopus robot, how it moves. So can we have, sorry, it's not an octopus robot. This is my desire to have an octopus robot. This is an octopus. And so can you imagine having robots that are as dexterous and flexible as the octopus? Or look at this elephant that is able to exhibit delicacy when it picks the banana from the child. And yet this elephant trunk can move with the strength required to whip a challenger. And so can we have robots that are both delicate and strong? Now, natural systems are also very good at exploring compliantly the environment. Just look at this elephant trunk exploring to find food. And so can we have flexible and agile robots that can do similar things? These are some of the questions that have been guiding the research of my group in the last few years. And in particular, these questions are inspiring us to rethink what is a robot. And I'd like to observe that while the past 60 years have defined the field of industrial robots, have empowered hard-bodied robots to execute complex tasks in constrained industrial settings with fixed programs, I believe the next 60 years will be ushering in robots in human-centric environments, and our time with robots helping us with physical tasks. And I'd like to also observe that I believe that while the industrial robots of the past 60 years have been mostly inspired by the human form, the next stage will be robots inspired by the animal kingdom and the built environments with the form diversity and the broad application potential. And so let me say a few words about why I am optimistic about this path forward. So the first point is we are making tremendous progress on materials. And this is allowing our machines to come closer to the systems we see in nature. Now, in the recent past, the soft robotics community began to believe in this new type of robot we call the soft robot. And the idea here is to bring materials and machines closer together, with materials becoming more intelligent and machines becoming softer and more agile like materials. But what is soft really? Well, soft refers to the body of the robot, and soft materials are the key enablers for creating a soft robot. And the way we measure the softness of a material is through Young's module. And in particular, natural organisms and soft robots, we would like them to be in the same range of Young's modulus measurements. And this is orders of magnitude lower than the Young's modulus for traditional robots. So here is another close-up of our robot, Sophie. This is an example where Sophie is descending in an underwater cabbage patch. And the robot's control system consists of dive planes that allow it to go up and down the water column. And there's this tail that is a 1 degree of freedom soft actuator that allows the robot to propel forward. And the actuator of the robot essentially is made out of silicone. The silicone has some cavities and an inextensible constraint. And the idea is that by pumping water or air inside this cavity, you can get a curvature, and then we can control how this curvature evolves, and that allows the tail to flip back and forth. Here you can see a close-up of what's inside the tail of the robot. The tail has these two chambers with ribbed structure for pressurization, and the inextensible constraint is in the middle. And then maneuvering is accomplished by moving water from one chamber to the other using a pump. And if you put the same amount of water in each chamber, the robot will move forward. If you put more water in one chamber than the other, then the robot will turn either left or right. So here is again the fish in action. You can see we have a gaming console that we adopted for underwater operations, and we give the robot high-level task commands, and then the robot is able to navigate autonomously towards carrying those task commands. And you can see how the console works. The fish is executing a left maneuver in this case. Now the fish has a fisheye lens camera that allows us to get observations remotely without being there, without disturbing the ecosystem. And this is really exciting. Now, the same control principles that we have used for the fish can be used to make soft fingers and robot hands. And here you can see a very early example of a robot with soft fingers. And you can see how compliant these fingers are. So you can think of each of these fingers as being a kind of a half a fishtail. This robot is able to pick up objects without knowing their precise location and without knowing their geometry because of the compliance that is embedded in these new materials. There are many challenges in designing soft robots. So for instance, the power and control hardware of the soft robots needs to be within practical uses. The manufacturing and materials need to be integrated with sensing. And then we need to develop the control system for these systems. And building the control system is very challenging because rigid body control does not apply directly to these systems. So what we have done in our lab was to think about ways in which we can integrate the sensors or the introduction of sensors into the molding and fabrication of soft robots. And here you can see a manipulator that has embedded sensors and that can tell whether it has grasped an object or not. And this is done by a method we call 3D embed printing. And this method allows us to use a 3D printer to add the sensors we need in each of these fingers. And in particular, we have curvature sensors, we have inflation sensors and contact sensors. And this is how it all works. You can see that we have a process that allows us to add a fugitive ink to the silicone molded material while the material is curing. And this is really exciting because using this approach, this printed approach, is a very natural way of incorporating sensors that have flexibility, that have elasticity, that are able to support our needs. And it's also a very simple process to deliver on. And so here's again what each finger looks like and what the sensors we have included in the finger look like. So we can differentiate between whether we have tip only inflation, base only inflation, tip and base inflation. We can differentiate contact along the finger and at the base. And we also have curvature sensors that show us how stretched the robot is. Now, okay, so we have these sensors, but the question is, what can we do with these sensors? And can we imagine creating a system that allows these continuous sensors that are embedded in the body of the robot to give us automatic measurements of the configuration of the robot? So in other words, can we make these sensors be globally proprioceptive, so we know the pose of the robot, because that will actually give us information about the environment and will give us a handle on how we can do control. And in particular, is it possible to go from these simple linear sensors to more surface-like sensors? And here you can see another method we have developed for incorporating sensors we call kirigami. And the idea is that we can build the skin where the sensor response is dependent on the cut pattern. And we can in fact learn how to associate the sensor response, the skin response, with the proprioceptive shape of the robot. And the way we have done that was by coming up with a model that describes the continuous soft robot. We started with a piecewise constant curvature model. But then we have actually found that this particular parameterization leads to singularities that are not suitable for learning. So we have replaced our parameterization, and we have been able to use this approach essentially in a data-driven fashion. We provide our robot, we put visual markers on our robot, and we show examples of the relationship between shape and sensor values. And from this, we can actually use a machine learning algorithm to really to train a neural network that directly learns to associate sensory values with geometric configuration. And so now we have intelligence. Not only do we have soft robots with perceptual skin, but we also have robots that know what configuration they're in, and this is good for control. The other thing we wanted to do is to address the strength of our robots, and if you recall, the design of the fluidic actuators, these actuators are not very strong. They cannot hold very much, and you have to put a lot of energy in order to retain a shape. And so we had the idea of combining soft outside skin with harder inner skeletons, like you see in these images. And the inner skeletons look a lot like origami. It turns out that you can do a physics analysis of the forces that can be generated in this fashion, and it turns out that by embedding these skeletons inside the soft robotic body, we can get robot systems that can lift up to hundreds and even 1,000 times the body weight. And this is because of the interaction between the edges of the skeletons and the skin of the robot. And the actuation principle is vacuuming. So it's not pressurization, it's vacuuming. And it turns out we can exert some really strong forces, and we can generate natively various types of degrees of freedom. So you can see a rotational degree of freedom and a contraction degree of freedom, depending on the kind of skeleton you can put inside. So you can design robots that have degrees of freedom naturally embedded in their bodies. This makes the control problem much easier. And so, and then you can combine them. So here you can see a linear actuator and a rotational gripper that allow us to formulate a different image of a robotic manipulator that is both strong and compliant. And here you can see a muscle. This what we call these things artificial muscles. You can see a 3-gram actuator lifting 3 kilograms. So we can design different types of grippers using different patterns. Here's one we call the flower gripper, and here is another version of the same made out of a different material. So now you can see how these robots can actually grasp. So we're very excited about the possibility of using new materials and using approaches that allow us to design intelligence into the body of the robot. And this is one way of moving forward and building more capable soft machines that go beyond the scope of operations of industrial manipulators. Another solution for building more capable robot bodies is also inspired by nature, and it's inspired by the observation that organisms in nature are made of cells that combine in different ways to make organisms like snakes and ants and organs like lungs and hearts. And the question we've been asking for many years now is, can we have robotic cells that can be composed in different ways to make different robot algorithms. Then the robot could take the best shape required by a task. For instance, you can have a snake that could crawl through the tunnel, or you could have a kind of a slinky form to climb stairs. All right, so the idea is that if the robot needs a screwdriver from a shelf that's too high up, the robot could change its internal geometry to reach high up. So as the goal changes, the body of the robot can change too. And here's a simulation we did a long time ago. This was in the late 90s, early 2000s, and it's a simulation that shows how a couch robot could become a dog robot. And in this case, the cell is a cube that expands and contracts by a factor of 2. And what you should get from this simulation is that the computation, the algorithms that are required for shape transformation have come a long way. But we still need to make the cell. And we do not know how to make the cell at the scale where the couch will be comfortable to sit on. Now, you might not need a dog couch, but what if I told you that in the future, I could give you a bag that has any tool you want on demand? And so in this conceptualization, the bag's smart sand makes a copy of a wrench. When you are done using the wrench, you can push it back in the sand and recycle the particles. Well, this is the dream. And so how far are we in the development of the dream? Well, I would tell you that today's robot cells are still too big to make a comfortable dog couch, but we can make simple things. We can make shape-shifting trusses, we can make support beams. And here you can see an example from our robot M-Block. This robot is a 2-inch by 2-inch cube that moves by pivoting. And the secret to the movement is a flywheel that's inside the robot. And this flywheel spins very fast. And then there's a braking mechanism that stops it suddenly. And the stored momentum then propels the cube forward. You can see another version of this cube. You can kind of see a little bit inside. You can see the mechanism. The flywheel can be oriented along different axes so that you have movement along the X, Y, or Z axis. And so this is really cool. We're very excited to have the M-Block, but the M-Block is still not going to give us the comfortable couch. And so then we started thinking about, rather than making small things, can we make bigger things? And so while we can't have comfortable modular couches, we might be able to do big applications, like perhaps we can have robotic boats that can carry people and goods, that can self-assemble to make, for instance, autonomous platforms for people to gather for events, or water-based bus stops or bridges on demand. And so the concept is that you might have robot boats, they assemble to make this platform, and then when people arrive, the people are have a step to go onto before they go to shore. And then maybe you can add manipulators to these platforms, and with these manipulators, you can move some of the infrastructure operations to autonomous operations on the water at night. So how far have we gone with the concept of making modular robotic boats? Here's an example where we have achieved a robotic boat at the quarter scale we wanted to get to. But you can see that there are multiple independent platforms. Each one can move independently, and yet they can connect with each other, and then they can move together. They can combine the thruster action to move in a coordinated fashion, which is very exciting. And so we have tried a number of different designs for these platforms, but ultimately where we want to go is a full-scale platform. And here you see the full-scale autonomous robotic boat that has been deployed in Amsterdam. And this boat has the same sensor suite you would see on a self-driving car. and it has the same algorithms for navigation, localization, map making that you would have on a self-driving car. And it's not quite like it's not quite as easy as taking the software built on a car and putting it on the boat, because the car moves on a straight surface, and now the boat actually moves on water, and there are waves on water, and the dynamics of the boat changes according to how many people are in the boat. But the point is that it is possible to imagine a robotic cell that will be an autonomous boat, and that could achieve this idea of on-demand creating platforms and bridges. And so we're very excited about the potential of this application and are continuing to work on it. So we talked about materials that give us better capabilities. We talked about whether we can make robotic cells. And while we continue to work on robotic cells, we have started a parallel second option because I don't know how long it will take until we develop the foundations to get these robotic cells to be truly universal. But so instead, we had the idea of developing the coding tools that will automate the design of custom robots and the making tools that will automate their fabrication. So rather than having a universal robot, we will be able to make very fast robots that are customized for the task that they have to do. And I hope that this can take us closer to a world where people will have a robot for any physical task. And here's how this could work. Let's take a user who's not a robotics expert. Let's call her Alice. We'd like to give Alice the power to automate many tasks in her home. So let's say Alice wants a playmate for her cat when she's at work. To do so, Alice could go to a store we call 24-hour robot manufacturing, where she could have a rough idea of what she wants. She could explore the design space. And once she settles on the design, the robot can be fabricated and the cat will have a playmate. And this process, the idea is for this process to be fast and inexpensive. And so my research group at MIT is working on this problem. And here's how we're approaching it. So let's say Alice wants to play chess with a robot. The idea is to provide the functional specification of the robot. And from this functional specification, we could determine behaviors such as pick up piece, move piece, drop off piece. And then from these behaviors, we can generate mechanisms that can implement those behaviors, assemble components, print the components, and we are done. And here is a robot that was developed in almost an automatic fashion. And we call these robots origami robots because they're created by folding and were inspired by the ancient art of origami. So origami robots can be fabricated flat and folded by hand, but we can also automate folding to create robots that can run, carry a load, and travel very fast, travel at 4 body lengths a second. And so here you can see our robot that starts like a piece of plastic with very specialized design. And when this plastic gets heated, the robot lifts from 2D to 3D and can now do interesting things. And when the robot is done with its task, the robot could go to recycle itself. And so I don't know if you're aware, but there are over 50 million tons of waste generated every year. And the big problem with most electronics is that they can't be recycled and they're toxic when they're discarded in developing countries. We should really think about making robots that will not create electronic waste. So I'm going to skip this. So we can make these robots at the small scale and at the large scale. But even at the small scale, the robots can be useful. And so, for instance, in this example of what we call the origami mini surgeon, we are building a custom robot to remove button batteries that have been swallowed accidentally in the US 3,500 people swallow button batteries every year. These are the batteries in toys and in watches. And the problem is that these batteries pierce the stomach tissue very fast in 60 minutes. And the only way to remove them is through surgery. And this is not an easy option. Now, what if we could have a mini robotic surgeon that we can imagine creating in the shape of an origami structure that could be squished into a pill size system? This pill size is about the size of a regular pill, but now it's made out of ice. And the idea is that you swallow this pill. When it gets to the stomach, the ice melts, the robot deploys, and now the robot can be controlled using an external magnetic field to get the battery, to pick it up using an embedded magnet, and then to eliminate it through the digestive system. And so here you can see the robot in action in a simulated stomach. And you can then send a second robot that could patch the wound and deliver medicine at the location of the wound. And what's interesting about these robots is that they're made out of food. These robots are made out of sausage casing. And as a result, they're not toxic when you swallow them. So you can imagine using this technology in the future to obtain tissue samples, to stop bleeding, to get better views inside our bodies, all of this without incision. So how do we automatically design these robots? Well, here's the idea. We can create any 3D object, for example, this bunny, by folding layers with the correct geometry, so that when you stack up the layers, you end up with a geometry of the desired object. And we actually have algorithms that can do automatically all these steps. And here you see the folded layers, 3D laser cut, and these layers, you can see it's very interesting. They create some built-in degrees of freedom for controlling the robot. And with this approach, we can take any regular object from the environment and make it animatronic and roboticized. And so, for instance, you can take the Sydney Opera House and turn it into a robot. And if the Sydney Opera House were a robot, this is what it would look like. Let's listen for just a minute. So we can take these approaches to designing robots, and we can turn any object in our built environment into a robotic system. And I'm really excited about this because ever since I was a kid, I really wanted to be like Mickey Mouse in The Sorcerer's Apprentice. And remember how Mickey Mouse summons the broomstick and then controls that broomstick through gestures? Well, the computational design and fabrication methods that we can develop today, coupled with intuitive human-machine interaction methods that monitor your gestures, can be used to get the Mickey superpowers of magic. So each one of us could become the magician, but now without magic, rather with computational approaches that allow us to do these kinds of tasks. So we have another method for automatically designing robots, and this method is inspired by computer science. It's a grammar-based method. And the idea is that you could take all the possible components that exist, put them in a database, and then create a grammar that talks about how the components can be connected to one another, and that add constraints on the task that the robot has to do. So here you can see an example for creating a legged robot optimized to do various manipulation tasks. So for instance, here is what comes out of doing search, machine learning and optimization on a set of designs using a set of set components. And you can see that the system comes up with very different designs if the task of the robot is to jump or to jump upstairs, to run as fast as it can, or to jump over gaps. And we can take the simulated examples and then go back to our components that define the library. And this way, we really accelerate the fabrication, the design and the fabrication of custom robots. So I have just a few minutes, and I do want to say a few things about the brain of these robots. We talked a lot about the body and how we use computation to design it. But I do want to say a little bit about the brain, and in particular, how we can use machine learning to get these new robots to learn how to control themselves. In the last example I have shown you, we actually have co-design of the body and the brain. And so the machine learning system that searches the design space, searches with the objective of a particular robot task. Now, in general, when we use machine learning in robotics, we have a number of issues that we need to deal with. First of all, data availability. Machine learning today requires massive data sets, and these are not easily obtainable in robotics. The data quality has to be very high. The cost of computation is non-trivial. And we end up with black boxes. We don't really understand how they work and that have brittle function. And the question is, can we do better? And I want to show you an approach for how to do better. And I'd like to show that approach in the context of learning for self-driving vehicles, because I think a lot of you are familiar with this problem. And so, but this approach can be used to manipulation or any other robot task. So the classical approach to autonomous driving is to take the problem and break it into sub-problems, solve each problem individually, and then connect the problems and connect the solutions. And this approach is challenging because you really have to come up with parameters for each type of environment where the robot operates in. And these parameters have to be done for each sub-problem and also for the connection between the sub-problems. So if it's nighttime driving or urban driving or country driving, all of these situations require different parameters. We've been interested in going directly from sensor data to actuation because this does away with the need of manually figuring out the parameters. And in fact, we have done this. We have successfully developed an end-to-end learning approach that enables us to drive, and it enables us to train vehicles in one environment. This one was trained in an urban environment, and here it is going through a country environment, very different than where it was trained. So this is very encouraging. But if you look under the hood, here's what the machine learning engine that decides how the car should steer and accelerate look like. And so let me orient you. Bottom right corner has the map. Upper left corner has the camera input stream. Bottom left corner has the attention map. We have some convolutional layers that interpret the camera input stream. The decision-making engine is this big rectangular box with blinking lights. And there are over 100,000 deep neural network neurons and over 500,000 parameters that combine to determine how the car should steer. And even though the action seems to be pretty robust and reliable, I will call your attention to the attention map, which is quite noisy. And I will say that it's impossible to figure out any patterns between these neurons and the final decision of the car. And so in my group, we have begun to look into whether we can have better ways of doing machine learning for safety critical applications like the ones we see in robotics. And we have come up with a different approach to the neuron and also to the architecture of the network. The new neuron we are working with is called a liquid time network. And in a liquid time network, the neuron has a differential equation rather than a step function inside it. And this differential equation can have variable time. And the architecture is something we call neural circuit policies, where we can specialize the neurons, and we're able to go forward and backward with the edges. And so now with our NCP architecture, look at how we can solve the autonomous driving car task using only 19 neurons. And look at how clean the attention map is in this case. So we have reduced the size of the network from over 100,000 to 19 nodes. And now we can inspect these 19 nodes. We can see how they fire, and we can associate decision trees with the performance of this network. And so I'm very bullish about the idea of exploring new approaches, new architectures for machine learning, because what we have now, the deep neural networks, are decades old ideas that have been enhanced by data and computation. But for safety critical applications, it's actually important to be able to understand how the network makes decisions. I'll show you another example. Here is an example for flight, where a 9-node neural network is learning to fly safely in the canyon and hit targets. And if you want the full degrees of freedom, then it takes only 24 nodes to do this very complicated task. So very exciting opportunities for developing new robots are ahead of us. And I hope that the examples I have shared provide us with a good starting point for reimagining robots, for what they look like, for what materials they're made of, and for the kinds of things that they can do. And I want to go back to what I observed, that I really believe that the next 60 years are going to usher in the age of adaptive soft robots and pervasive robots with form diversity, material diversity, and a wide range of capabilities. And the current generation of students, are going to be the inventors that will make this dream come to life. And so today, if you can think about the concept, you can write it on paper. But imagine a world where if you can think it, you can make it, and you can breathe life in it through programming. In other words, a world where anybody can make their own robots, customized to tasks, customized to ideas that save lives, improve lives, carry out difficult tasks, and take us places we can't physically go to. And in this world, we will be supported by cognitive and physical tasks by robots. And so what's not to love? Now, before I end, I just want to say that I've shared ideas that span a number of years of working in robotics. And these ideas were developed with my brilliant students and postdocs. And here are some of them. And with this, I am going to stop sharing, and I'm happy to answer questions.
Fantastic. Thank you so much, Daniela. So very inspiring talk. And I want to ask the audience to just feel free to write your question on the chat for Daniela, if you have any. And I probably want to start to ask you a question, like with respect to going toward the vision that you show us, do you think that we need to push more on the body side or more on the intelligence side? And where do you see the majority of challenges in the two aspects?
Well, I really think that we have challenges in how we make robots. We have challenges in how we think about the robot brains, and we have challenges in how we interact with robots. I did not have time to talk much about the interaction, but I will say that right now, it's mostly the case that you have to be an expert in robotics in order to use a robot. And with most things we do, we adapt to the machines. They don't adapt to us. And so an important area of research for robotics is developing technologies that allow people, that allow robots to adapt to people rather than the other way around. An important aspect in building robotic bodies is really making this process higher level, making this process more abstract, because if we have to tinker at the level of screws and nuts, it just takes way too long. I kind of want the compiler for robots. I'd like to be able to say, I want a robot that will do some high-level task that I could specify in intuitive language. And then from that specification, I want to I want to get the design and the fabrication approach for the robot. This will allow us to accelerate what robots we have and how we customize the robots. The robots we have today are really either boxes on wheels or they're inspired by the human form. And so thinking outside of the box, so to speak, and thinking about robots that have different shapes, different material variety will give us instruments that are much more fine-tuned to what we want these machines to do. And we have so many materials available to us. It's not just metal and plastic. We have wood, we have plastics of different types, we have food, we have paper. We should take advantage of everything we know in order to make machines. But we don't have the robot compiler yet. I've given you some examples of small steps we have made towards creating these rapid processes for making machines, but there is so much to go in this respect. And then the control systems for these robots, the intelligence of these robots is an area where there is so much opportunity for work. And there is a lot to do with low-level control of robots. I did not spend much time discussing that. I hinted that you can use machine learning to get a soft robot to understand its body configuration. And this is important because if you're rigid, then you move and then you know exactly where every component of your body is. But that's not the case with soft robots. So low-level control remains a challenge for soft robots. But then we'd really like to elevate our control systems of machines to get to task level control and to get to the point where we have machines that learn, but that learn in a way that is explainable, that learn in a way that is easy for humans to understand. And this is absolutely critical for safety critical applications. If we're going to use deep learning, we're going to end up with a kind of huge engines that I have shown you in the context of our autonomous vehicle. Now, experimentally, our deep neural network solution seems to work pretty well, but we don't understand why. And it's so difficult to try to look inside that box to figure out exactly why. On the other hand, if we stretch our imagination and come up with new ideas, new models for learning, then maybe we can get to the point where we address some of the big challenges with machine learning today. And the challenges are too much data, not robust behavior, not explainable behavior, and also kind of low-level behavior. All of these need to be addressed at a different level for a safety-critical application like a robot. Like, I don't mind having an AI system classify my photos from my holiday, because if they make a mistake, if that system makes a mistake, it's no big deal. But I don't want a machine learning solution to crash my robot.
Yeah, And I have actually a question from Maurice. He said, in terms of sensing and perception, these robots are very difficult to use in traditional perception mapping, state estimation paradigm. Is there some to bridge the gap, for example, with learning-based perception? What are your thoughts on this gap?
Yeah, I think that there are things for which the math works, and there are things for which the math is difficult. And so in particular with soft robots, the math is not there. We don't actually have good solutions for controlling our soft robot systems. We have some approximations, but those are not really, like, I would say that they're okay solutions. I would say that we need to stretch ourselves to work harder to get something better. And so, and similarly, if we want to understand the natural world, it's like we don't have the equations. So there are problems that are really not amenable to what we can do with equations, but where learning becomes critical. And so for me, the question is, how do you learn? And the question is, if you learn something, is that safety critical? So can you afford to make mistakes? If you learn something and you'll make a mistake from time to time, or is it a safety critical application, in which case we should really try to find solutions where we get explanations and understanding of how the system does it. And so I think that there is such richness of problems here, because on one hand we can have things, we can have solutions, but on the other hand, are they the best solutions? Can we get better solutions?
Thank you so much, Daniela. And I wanted just to ask another question about, like, in terms of computation, do you think that, like, we can actually use the body to, in part, solve this kind of aspect, and if this can be in a certain way programmed, when, like, you show us that the person can actually decide the behavior of its robot, and like how do you envisage the fact that we can actually download part of the computation in the body?
Yeah, so I guess that's how. So it's interesting to think about how much computation should be in the body and how much computation should be in the brain. One reason why soft robots are so good for manipulation is because part of the computation is indeed done in the body. Like, you know, I have this, I can grab this water bottle without actually describing precisely where the bottle is located and what the shape of the body is. And I can do so because my body has compliance. And similarly, soft robots, soft robot hands have compliance. Now, in contrast to soft robots, the industrial manipulators need to know very precisely where everything is located, and they calculate very precisely every single maneuver. So you have tremendous engineering that yields extraordinary computations, but in that case, the body doesn't really do much. And when you actually make a mistake in the placement of the object, that system will fail. But a compliant body that can do morphological computation, like a soft robot hand, will be much more adaptive, will be able to tolerate imperfections and errors. And this is absolutely needed if we want robots to be with us, if we want robots in human-centric environments.
Okay, thank you so much for that. I think that we are now at the end of the seminar. So again, Daniela, thank you so much for the inspiring talk and this amazing discussion. And so I think that we hope you can come back and visit Oxford, maybe.
In person sometime, yes.
Yeah, please.
With great pleasure. So thank you so much for inviting me, and I look forward to continuing the conversation. Yes. And in the meantime, for all the students in the audience, This is such an extraordinary time for you to become the inventors of the next generation of robots. And I will just recommend to not settle, to really use your imagination and creativity to push the boundaries, to invent new machine learning algorithms, to invent new types of robots, and to really think broadly about how extraordinary it would be to have these intelligent tools that support people with cognitive and physical work. Thank you so much.
Thank you, Daniela, and thank you everyone for joining us today. Bye.
Thank you, Perla. Bye-bye.